In this video, we're going to introduce internal direct products. And the motivating question for why would you study such a thing is, how do you determine, given a group, that is isomorphic to the direct product of two other groups? Why would you want such a thing? Well, for the same reason it's nice to be able to factor a large number as a product of smaller numbers. It's the same concept. You've now replaced a large group with two smaller groups. Sometimes it allows you to turn questions from a larger group to questions about smaller groups. So last time we discussed internal direct products. Here's the big theorem about them. If G is the internal direct product of H and K, then G is isomorphic to the direct product of H times K. So this is the reason why we care about internal direct products. It's a way to discover that your group decomposes up to isomorphism as a direct product of smaller groups. So here are two corollaries of this fact. Based on the examples we just did in the previous video, if you've got a dihedral group of order 2n, where n is odd, then we saw it was an internal direct product of these two subgroups. One generated by the 180-degree rotation, and the other one generated by even rotations and one of the reflections. I pointed out that the second group is isomorphic to the dihedral group of order n, well, of order 2n technically, and the other one's just C2. So in this case, this dihedral group is actually isomorphic to a direct product of smaller groups. Likewise, if the GCD of A and B is 1, then you can actually rewrite Z mod AB as this internal direct product, which means, according to this theorem, it's also isomorphic to this direct product of these two cyclic subgroups. The first one is, we said, was a cyclic group of order A, and the second one we said was a cyclic group of order B. So we now see that this cyclic group is isomorphic to a direct product of cyclic groups, which was one half of that if and only if theorem. So we only need to show the other half. And we show the other half by showing what happens if the GCD is not 1. If the GCD is not 1, then the least common multiple is not AB. We'll let M be the least common multiple of A and B. And you can take any ordered pair in this direct product, and you can check that the mth power is going to be c to the m d to the m, because m is a multiple of A. The a c to the m is the identity, because m is a multiple of B. D to the m is also the identity. And so we see that no element of ZA cross CB has order A times B. Why? Because their order is at most M, and M has to be smaller than A times B. And so none of the orders are big enough to include every element of the group. Therefore, we've actually proven the full theorem that Z mod AB is isomorphic to the direct product of ZA and ZB if and only if the GCD of A and B is 1. So all I need to do to finish that proof is to prove this more general theorem about internal direct products. It's worth pointing out the theorem actually gives this isomorphism directly if you are interested. I just prefer this approach because we discuss internal direct products anyways, and I find this to be a useful application of this abstract result. Alright then, so let's go through this proof. We want to prove that these two groups are isomorphic. Well, in order to do that, we better define a bijection. It's not clear how to define the bijection this direction. I mean, I know G is equal to the product of sets HK. And so I know there's existential quantifiers. So I know G is equal to HK, which tells me for all G there exists a little h and a little k. So that tells me I could theoretically define phi of G to be little h, little k. But problems with existential quantifiers is that has to do with well-definedness. How do I know there's only one choice of h and one choice of k for which this equality holds? The answer is I don't, at least not yet. And so it's not clear at all that such an idea is well defined. So I get stuck if I go this direction. But it's worth at least thinking about it, because that's good as a mathematician to think what the issues are, because that explains why we do the proof the way we do it. This approach seems to be complicated because you run into well-definedness problems. So instead we go the other direction, because it's easy to say, well, given an ordered pair little h and little k, how can we define an element in G? Well, h and k are elements in G, and we know how to multiply. So how about we just define phi of an ordered pair to be their product? I mean, it might not work, it might not solve our problem, but hey, at least it's a function. Let's see if it works, and let's hope for the best. Let's check that it's multiplicative. Take two elements in the domain, they're ordered pairs, where the first coordinates are in the first group, h, the second coordinates are in the second group, k. So I'm going to call the first coordinates h and h prime, the second coordinates k and k prime. Then phi of hk times phi of h prime k prime. By definition, phi of hk is h times k. Phi of h prime k prime is h prime times k prime. Let's see what happens when I apply phi to this product of ordered pairs. Oh, what is the product of ordered pairs? It's component-wise multiplication. It's an ordered pair whose first coordinate is the product of first coordinates, h times h prime. Second coordinate is the product of second coordinates, k times k prime. Phi just sends this ordered pair to its product. How do these two elements differ? In the middle. K times h prime versus h prime times k. Oh, but I remember I have this commutativity condition. Nothing says that I couldn't be using a prime here. I can apply this formula to the case h prime k. And so applying this formula to this particular case allows me to conclude this equality. And since this equality is true, these two functions are true. And so phi is multiplicative. Note that this is not what I would expect as a final draft for a proof. This is what you call thinking out loud. I should have a let hk be in hk, let h prime k prime be in hk, and I would probably go rewrite this. So this would be step 1, to step 2, to step 3. And then I'd put the explanation for 2. separately. Just worth pointing that out. So it's always worth pointing out. Sometimes when you're doing scratch notes, you do things one way, but once you do the final draft of the proof, you write it in a way that's easier to follow for the grader. And of course, if you check the textbook actually does do it in the final order that you're supposed to. But we're at a point in the course where it's good to try to show how a mathematician thinks out loud. All right, how do you show the function is surjective? Because we want to show it's an isomorphism. Well, let G be an element in the group. Since G is equal to H times K, because remember, we already know that it's an internal direct product, little g has to factor as little h times little k. Well, then that means phi of this ordered pair is going to be little g. So my question about well-definedness goes away if I work the other direction. Now let's check injectivity. All we have to do is suppose that the function takes two inputs and sends them to the same output. Suppose phi of two ordered pairs are the same. So phi of hk equals phi of h prime k prime. Then that means h times k is equal to h prime k prime. Well then, let's multiply both sides of the equation on the left by h inverse and on the right by k inverse, mainly so we can get the identity on one side. And what do we get? We get h inverse h prime times k prime k inverse is equal to the identity. Well, this first element is an element in h, and the second product is an element in k. So we see another approach is that if we move the elements from h over to the other side appropriately, as follows, we have h prime inverse h is equal to k prime k inverse, which means we have an element in h is equal to an element in k. And the only way that happens is if this element is actually in the intersection. But the intersection of h and k is the identity element. So that means this product, h prime inverse h, is the identity. So h prime inverse h is the identity, which is also k prime k inverse by this equation. And so this equality here tells you that h is equal to h prime. This equality here tells you that k is equal to k prime. So these two ordered pairs have the same first coordinate and same second coordinate, and therefore they're the same ordered pair. Therefore, phi is injective. Phi is surjective, and phi preserves the multiplication operation, so phi is an isomorphism.